Hi there, welcome back to this channel. In this video, we are going to be considering the idea of limits and continuity, which is a fundamental topic you must understand if you will really understand the idea of infinitesimal calculus. And stick with me till the end of this video because I'm going to be exposing the idea of limits and continuity to you, even using graphs. Is that okay? Now what is a limit? Now think of this line, for example, as a particular number, as a particular barrier that this arrow is going to touch. Now, what happens is this, that every time this arrow moves, this guy also moves in a kind of way that almost never allows the arrow to touch it. So what that means is that this arrow will keep going further and further, trying to touch this wall or this barrier, but it never really gets to that barrier. It never really touches that barrier, only that it keeps getting closer and closer and closer to it. Is that okay? All right. So now, having understood the idea of limits, that it is the boundary that a particular value is trying to approach, a particular thing is trying to approach, but it never really gets to that boundary. Okay, now let's set the ball rolling now. Now, how do we define limits technically? Now, the limit of a function at a particular value of a variable is that constant or number that the function approaches as the variable approaches a particular value. So such that the difference between the constant and the function is so small that we say it is almost it is almost zero. So what we are saying is basically that function is going to approach a particular constant or a particular number, which is as a result of the variable that has been plugged into the equation, is also approaching a particular number. So that function is approaching that particular number. I'm going to put that in context, but let me first show you a graph. Now look at this graph. Now, basically, we're going to be using piecewise functions. Is that okay? Because it's one of the ways by which the idea of limit and continuity came about. Now, for piecewise functions such as the one of 1 over x, the graph of 1 over x, if f of x is equal to 1 over x. Now, what we're going to have is a graph that has two asymptotes, horizontal and vertical asymptotes in the positive quadrant there, and vertical and horizontal asymptote again in the negative quadrant here. Now, in this case, just follow me, you're going to see that these are x-axis and these are f of x axis or y-axis, okay? Now, you're going to see that as our y value decreases, as our y value gets closer and closer to 0, what is our x value doing? The x value is going closer and closer to positive infinity, but never really touches infinity. It's going to go, as the y value reduces and gets closer and closer and closer to 0, you're going to see that the x value rather, keeps getting closer and closer to positive infinity. And of course, in the same way, as our x value also decreases, in the other time the y value decreases. Now, our x value is now decreasing. As our x value tends towards 0, our f of x value becomes closer and closer to infinity. Now, how do we write that mathematically? As our x value becomes 0, the limit of our function f of x is positive infinity. So what this is saying is that this function never becomes infinity, but our function keeps approaching infinity as our x approaches 0. So this is the mathematical way, notation that we use for writing limits. Is that okay? So, and in the other case also, as our x value tend towards infinity, our y value is tending towards 0, because the reason why I'm restating that statement that way is that our function depends on our x value. So if x value is increasing, so for every increasing value of x, y is what? Y is what? Is reducing. Y is, for every increasing value of y is reducing. For every increasing value of x, y is reducing. So what do you have? Because it's an inverse graph. An inverse graph. Okay, so what does that mean? In this case, you are going to see that as the limit of our f of x, as x approaches infinity, as x approaches infinity, is going to be equal to what? 0. Because y is becoming closer and closer to 0 as x is increasing. Does that make sense? X is increasing, but our function y is becoming what? Closer and closer to 0. Does that make sense to you now? So really, this guy never really touches 0. It never really touches 0, but it's going to become closer and closer to 0. That is our function. Now, this is the way we now write it. Of course, in this case, it is the same. The limit of this function, f of x, as x approaches 0. Now, there are two things here. You're going to see that x is approaching 0 here too, right? X is approaching 0 here. The same way here, we said x was approaching 0 here. So there are two sides from which x can approach 0, right? Okay. In this case, we say that the limit of our function as x approaches 0 from, this is the left-hand side, we use negative to signify the left-hand side. We use negative to signify the left-hand side. So we call it left-hand side limit. And we call this one, because we are coming from this side, we call it the right-hand side limit. So we say, we use positive to denote the right-hand side. Okay. Now, in this case, we are also saying, therefore, that as our x approaches 0 from the left-hand side, our function is going to approach what? Let's see. As our x approaches 0 from this left-hand side here, you're going to see that the value of our y is increasing towards what? Negative infinity. Negative infinity. And as our function approaches, the limit of our function as f of x, as x approaches, now, if we go in this direction, x is going to approach. If x is going in this direction, what is x doing? X is increasing, right? So as x is increasing in this direction, this is the rightward direction. So what is it approaching there? It's approaching negative infinity. So it's approaching infinity from the negative side. It's approaching negative infinity. Negative infinity. So as it's approaching negative infinity, our function is going to become what? It's approaching negative infinity. Our function y is going to become what? 0. Our function is going to become 0. So what does that mean? As you see that x is increasing, x is becoming the more negative, so that is reducing in value. What is x doing? Y doing? Y is increasing in value towards 0. From negative is becoming 0. It's becoming closer and closer to 0. So that is what we have. Now, here's the thing. We're going to see that for this one, we have 0 and we have 0, right? So, if you look at the limits of our function as it approaches 0 on the negative side, is negative infinity. The limit of our function as it approaches 0 on the positive side or from the right hand side is 8. It's positive infinity. So you are going to see that the left hand limit and the right hand limit are different, right? In such case, we say that the limit does not exist. When the right hand limit and the left hand limit are not equal, we say that the limit does not exist. So for a limit to exist, it means that both the right hand limit and the left hand limit must be equal. So this way we now write if we wanted to take limits from both sides, the one I wrote before, which is limit of f of x as x tends towards 0, is going to be does not exist. DNE means does not exist. Why does it not exist? It doesn't exist because the limits from this side does not equate the limits from this side. And you can see that in this piecewise function. Okay, so now let's now go there further into our notation. Now you can also see the same guy here. Now, if it approaches infinity from the negative side, if you say infinity from the negative side, we are coming from the negative side, that's from this side, right? We are coming from this side. Infinity from this side is going to be, if we are approaching infinity from this side, it means you can come from any value lower than infinity. But if you can't take from the positive side, is that okay? You can't take from the positive side. So, because there's no value that will be greater than infinity. So that's why when we use infinity, we don't use left hand or right hand. What we can have is positive infinity and negative infinity. I hope that is clear. Okay. Now, if that's the case for our limits, then now how do we write limits? So we said that our limit is going to be that constant value that our function is approaching as our variable is approaching a particular number. So let's say that our x variable was approaching a value c or a value a. So if our variable x is approaching a, then the limit of f of x as x approaches a is going to be equal to the limit. Okay, no. If we say it was L, for example, it means that the limit of f of x as x approaches a from the negative side is equal to L1 A, and of course this we write mathematically basically. So let's say this was A and this was B. We'll say that it means this limit of f of x is as x approaches A from the positive side should also be what? L. Is that clear? So the way we write this is that if the limit of f of x is equal to L as x approaches A, then these two values must be equal. That is, the limit that our function approaches from both sides, as x approaches a from both sides, must be equal to that same constant. And if not, then the limit does not exist. And of course, if the limit now exists, it means that our function is continuous at that point. So that is what brings in the idea of continuity. But I'm going to show us when we do a demonstration, a calculation on limit, then we'll go to graphical representations so that you can see continuity in the right context, in full context. Now, so I hope you understand this idea now, that if the limit exists, then it means that the limit from both sides must be equal. The limits from both sides of the x variable must be, or the limit of the function must be equal when we take x variable, when we approach x variable from both sides. Okay? Or when x variable approaches the value that is approaching from both sides. So what that means is that x variable is movable, isn't it? Okay. Now, let's take some properties of limits. Properties of limits. Now, what are the properties of limits? Now, the properties of limits are basically what mathematically correct statements about limits. Those are the properties of limits. So, the first one you want to know is that the limit as x approaches a of f of x plus of f of x plus g of x. Let's say this was square bracket of f of x plus g of x. The limit of this is the same as, is equal to the limit as x approaches a of f of x plus the limit of g of x as x approaches a. Do we understand that the limit of this sum is equal to the sum of the individual limits? Okay, that's number one. Now number two, the limit of f of x plus g of x as x approaches a, no, minus rather now, minus is equal or is also equal to the limit as x approaches a of f of x minus the limit of g of x as x approaches a. So what this is saying is that the limit of the difference is equal to the difference between the limits. Does that make sense? Okay. Number three, the limit of k, a constant times a function, as x approaches a value a is equal to the limit, is equal to that constant times the limit of f of x as x approaches a. Okay, quickly let's do some questions regarding these three rules that we have seen so far. We're going to be seeing 5 rules. Is that okay? Let me just quickly show you something so that it's not look like we're just writing principles. Okay. So for the first case, we said the limit of a sum should be equal to the limit of the functions. It should be equal to the sum of the limits of the functions. Okay. For example, if I said that f of x, if f of x is equal to x squared plus 2 and g of x is equal to 2x minus 1, for example, I now said find, to show this, for example, to show this, if my x was approaching 2, if x is approaching 2 in this case, you are going to see this, that the limit of f of x, which is the limit of the sum of this and this, that will be x squared plus 2 plus 2x minus 1. Does this make sense to you? Because this is what we have here, the function plus the function, the function plus the function. As x approaches 2, let's see what that will become. The limit of this function is going to be x squared plus 2x, then 2 minus 1, that is plus 1, okay? Then as x approaches 2, so the limit of this function as x approaches 2. Now let's take the limit. If x approaches 2 from both sides, we are going to use 2, which is the approximate value that since x is approaching 2, so it's going to be the approximate value that x will approach. So we say we plug 2 into this place, so we have 2 squared plus 2 times 2 plus 1. That becomes 4 plus 4 plus 1, which is equal to 9. So we therefore say that the limit of our function is going to be 9. The limit of f of x plus g of x as x approaches 2 is going to be 9, according to what we just solved. Okay? If that is the case, then let's prove. The limit of the function as x approaches 2 first. Let's see. What's the function? F of x f of x is equal to x squared plus 2. So the limit of x squared plus 2 as x approaches 2 will be what? So if x is equal to 2, let's plug that in, then we have 2 squared plus 2. That will be 4 plus 2, which is what? 6. Okay? Then for g of x, limit of g of x is 2x minus 1. 2x minus 1 as x approaches 2. So if that's the case, let's plug in our value there. As we plug in our value, we are going to see that 2 times 2 minus 1, and that will give us 3. This will be the case. Now, by the time you add, this is the limit of, if you now take the sum of the two limits, that's going to be 6 plus 3, which is equal to what? 9. So, we've proven that first row. Then, well, we don't need to prove the second row because it's basically going to be the same. Let's try and prove the third row. That is very simple too. Now, for the third row, we're basically saying that the limit, if f of x, let's say f of x is 3x squared plus 2. I want to multiply a constant by it. So the limit of 3 into bracket x squared plus 2 as x approaches 2 should be equal to the limit to 3 times the limit of the function x squared plus 2 as x approaches 2. Okay? So if this is the case, then we have that x squared, by the time we open this bracket, we're going to have the limit of 3x squared plus 6. 3 times x squared is 3x squared plus 3 times 2 is 6. So the limit of this as x approaches 2. So what will be the limit? When we plug 2 into that equation, we're going to have 3 times 2 squared plus 6. This becomes 2 squared is 4. 4 times 3 is 12. 12 plus 6 is 18. Okay? Let's see. If by the time we multiply 3 by the limit of this function as x approaches 2, if we are going to get 18. So if we plug in 2 into this equation, we're going to have 2 squared plus 2. That is 4 plus 2, which is 6. So 3 times 6 is what? 18. So it proves the third law, okay, or the third property. So let's go into, let's see other laws, other properties. Okay, so the fourth property of limit is we have considered addition, subtraction, and multiplication of function, then multiple. What if it's the third rule, the third principle is that if we want to take the limit of the multiple of two functions, so that is the limit of f of x multiplied by g of x multiplied by g of x as x tends towards a is going to be equal to the limit of f of x as x tends towards a times the limit, or more like just put it in brackets, the limit of g of x the limit of g of x as x approaches a. Okay? And this makes sense. This makes sense because remember our function f of x we said was x squared plus 2. So x squared plus 2, and g of x we made, let's just use anything, 2x minus 1. Okay, yes, this is what we used. Okay, so if this is the case, let's find this f of x times g of x. So f of x times g of x is going to be x squared plus 2 times 2x minus 1. If that's the case, then we'll have this times this will give us 2x cubed plus or minus this times this minus x squared plus 4x minus 2. Okay, so we cannot simplify this further. Yes, we can't. So the limit of this as x approaches, let's use 3, as x approaches 3 will be what? It will be equal to 3 cubed. That will be 3 by 3 by 3 is 27. 27 by 2, 54 plus minus x squared, that's 9, plus 4 times 3, which is 12, minus 2. I hope you know how I got all of this. I simply plugged in the value of x into this. Okay, if that's the case, then we have 54 minus 9 plus 12, that's plus 3. 3 minus 2, that's 1. That's plus 1. So that will be 55. Our function is going to approach 55 as x approaches 3. Alright, let's see if that will be the case with the limit of the individual function. By the time we multiply the limit of the individual functions. So the limit of f of x when that guy approaches a, when x approaches 3 will be what? Limit of f of x will be limit of x squared plus 2 as x approaches 3. This will be equal to what? If you plug in our 3 there, 3, the limit as x approaches 3 of f of x, that will be 3 squared plus 2 will be equal to 3 squared is 9 plus 2, that is 11. Okay, of course, you already see it can divide, so that one should give us 5, and that makes sense. Yeah, okay, let's just solve it. So the limit as 2x minus 1, the limit of 2x minus 1 as x approaches 3. So that will be equal to limit as x approaches 3 of 2 times 3 minus 2 times 3 minus 1. So that becomes limit as x approaches 3 of 6 minus 1 will be equal to what? 5. By the time you multiply both limits together, 5 times 11, you're going to get 55. So that proves that property of limit. Okay? Okay, then the fifth property of limit is quotient. That one is product or multiples, and this one is quotient. So, and it says that the limit of f of x over g of x as x approaches a value a is equal to the limit of f of x as x approaches a over the limit of g of x as x approaches a. Okay? Of course, we don't need to prove this again. That holds. That principle holds. It's just saying that the limit of the quotient of this function is equal to the quotient of the limits of each of the functions. Okay? Then the last rule, the last property is that the limit of f of x all raised to the power p, all raised to any power k. Okay. I want to m, let's use m. M is a fine number. Okay? So as x approaches a, the limit of f of x always by m as x approaches a is equal to the no, let's say it was redistributed. No, we are distributing this, it's still the same. But let's say it was something like this. Let's say it was the product of this g of x all raised to the power our m. Okay, yes. So this will be equal to the limit of x raised to the power, the limit as x tends to a of f of x all raised to the power m. No, the limit all raised by m times. Is that okay? Yeah, I remember what I wanted to write now. This is what I wanted to write. It's just a simple principle that as x tends to a, the limit of f of x all raised by m should be equal to the power of that limit. The power of the entire limit. Does that make sense now? So, but in other words, in this case, we can still split this power, distribute it for both of them. So when we distribute to this guy, to f of x, we have this. We distribute to this guy, we have the limit of g of x as x approaches a, or is power m. And that is going to be the case. Okay. So this is it for the properties of limits. Now, let's evaluate some limits. Let's see some methods of evaluating limits before we see what continuity is graphically. Okay? All right. So, now, just in case someone is beginning to think that to solve limits, all we have to do is just plug in the value of the function of the variable, and then we will get our answer. Now it is not always so. Is that okay? There are several methods that we use in evaluating limits, because sometimes when you plug in the value directly, you will get what we know as, or what we call indeterminate terms. Indeterminate terms, or indeterminate function. Indeterminate. So an example of indeterminate function is where you plug in the values directly and you resultantly get 0 over 0, or you get infinity over infinity, or you get a constant over 0. Now, of course, this one is already called undefined. Is that okay? Now, the reason why this is indeterminate or undefined also is because this, if you have 2 over 2, for example, 2 over 2 is what? 1 over 1, isn't it? Which is what? 1. In this case, do we say 0 takes care of 0 and then we get 1? We're not sure. Do we say 0 over 0? That is 0 divided by 0, because if I divide 0 by a constant, it should give me 0. So should I say this will be 0 also? Or, it's just not defined. Is that okay? So that is why the method of just substituting the value of the variable into it doesn't always work. So we have several methods that work though. And here are the methods. Now the first method, of course, as you rightly guessed, is the method of direct substitution. Direct substitution. Now, how does the method of direct substitution work? Let me give you, let's take some examples. 7x squared minus 5x. Take the limit as x tends toward 0 of 7x squared minus 5x plus 1 Okay, oh, as x tends to 1. As x tends to any value, is that okay? So if this is the case, you basically directly substitute this. When you substitute this, you're going to have 7 into bracket 0 minus 5 into bracket 0 plus 1. Okay, so what do you have? 0 plus 0 plus 1. That's what? 1. So this function tends towards 1 as x tends towards 0. Does that make sense? Okay. We can also have the limit of a function 3x minus 2 over x plus 1 as x tends towards 5, for example. If this is the case, you directly substitute. So what do you have? You have 3 into bracket 5 minus 2 all over 5 plus 1. This becomes 15 minus 2 over 6. This becomes 13 over 6. And that becomes what? 2 over 1 over 6. This works insofar you do not get 0 in your denominator. That is, direct substitution will always work for this if x is never equal to 1. I mean, it's never equal to minus 1 rather. The only place, or the only condition where this direct substitution will not work is if for this function, this guy is minus 1. Because that will make the function what? Indeterminate or undefined. Okay. Now, the second method is the method of factorization. The second method is that of factorization. So consider this question, for example, that find the limit of x squared minus 9 over x minus 3, or maybe even over x plus 3, as x approaches minus 3. You are told to solve this. In this case, if you directly substitute, let's see what will happen. If you directly substitute here, it will be minus 3 all squared minus 9. Our limit as x approaches minus 3 of this will become minus 3 plus 3. And that becomes minus 3 squared is what? 9. 9 minus 9 over minus 3 minus that, 0. So we have plus that, 0. So we have 0 over 0. You see, this is what? Indeterminate. So we cannot use what? Direct substitution. So what do we use? We can factorize. Now you see, these methods that we use are basically methods of trying to simplify the function as much as possible in order to be able to get what we can work with, a simpler term that we can work with. So for example, in this case, let's simplify the function. And how do we simplify the function? We can simplify the function by factorization. And how do we factorize here? Remember that this is difference of two squares, right? Because this can be simplified to the limit as x approaches minus 3 of x squared minus 3 squared over x plus 3. And recall that if I have a squared minus b squared, this is going to become what? A plus b and a minus b. That is, if you multiply these two, these conjugates, if you multiply them, you are going to get difference of two squares. Okay, if that's the case, then we have limit as x approaches minus 3 of this becomes x plus 3, as we already have there. That is first term plus second term times first term minus second term. First term x plus second term 3 times first term minus second term all over x plus 3. If this be the case, then this takes care of this. Then our function has simplified to the limit of x minus 3 as x approaches minus 3. So we have, we're going to substitute this guy into this, then our function becomes minus 3 minus 3, and that becomes minus 6. Okay, I hope this is very clear. Okay, now let's go further. Let's say we wanted to find this, the limit of a function x cubed minus 8 over x minus 2 in this case, as x approaches 2. As x approaches 2. How do you take these limits? How do you take these limits? So, the first thing you want to do is that you want to re-express this. This becomes the limit as x approaches 2 of x cubed minus 2 cubed. Okay? All over x minus 2. Now remember, in identities, polynomial identities, that if I have alpha cube plus beta, or minus beta cube rather, alpha cube minus beta cube, a, that's just a cube minus b cube anyhow. Is that okay? I'm trying to use the root of quadratic equation. Okay, so if you have this is going to become a minus b, then close brackets, a squared plus ab plus b squared. I hope this is clear. Let me try to rewrite this. That remember that a cubed minus b cubed is equal to a minus b multiplied by a squared plus ab plus b squared. Is that clear? So if this be the case, then we can re-simplify this. Okay? We can simplify this to this form, so that this becomes the limit as x approaches 2 of this will become a minus b, that is first term minus second term. That will be x minus 2, open bracket, first term squared, x squared, plus ab, that is first term times second term, that is 2x, plus second term squared, b squared, that will be 2 squared, which is what? 4. Okay, all over x minus 2. So you see, in this case, we now have similar term up and down. Then we can do what? We can remove them, cut. Is that okay? Divide. Is that okay? So we have the limit of x squared plus 2x plus 4 as x approaches 2. Now, x can become 2 or can approach 2. So it becomes 2 squared, which is what? 2 squared, that is 4 plus 2 times 2, 4 plus 4. This becomes 12. Sorry. This becomes 12. So the limit of our function is what? The limit of this is what? 12. Does that make sense? Like, in the correct notation will now be that the limit of x cubed minus 8 over x minus 2 as x approaches 2 is equal to 12. So that's the correct way to write that. All right. Now let's take the next method of solving limits. Now the next method of solving limits is the method of L'Hopital's rule. Or no, let's take the rationalization rule first. The method of rationalization. Rationalization. Number 3 rule. Method of rationalization. So of course, for us to rationalize, it means there's going to be an irrational number or a set. Is that okay? So let's take a question. There's a question here which says the limit as x tends towards, as x tends to, what's this? As x tends to 0, okay. Or as y tends to 0, that's limit as y, let's make it b, as b tends to 0 of root a plus b minus root a all over b. Okay. So whenever you have an expression like this, the first thing that you want to do is you want to, rationalize this expression. So how do you rationalize this expression? You will multiply, it's minus, yeah? Not plus. Now you rationalize by multiplying both this numerator and the denominator by the conjugate of this irrational expression, and the conjugate will be an expression that has the same values here but different signs. Exactly, that will be the conjugate of this value. What that means is this: we multiply up and down by the square root of a plus b plus the square root of a all over the square root of a plus b plus the square root of a. So if this be the case, then this will now multiply everything here, and this here will multiply everything here. Now remember that we are taking limits as b tends towards 0. Okay, so this is going to be what we'll have. If you multiply this guy by this guy, since this guy is a plus b and this guy is a plus b, square root of a plus b times square root of a plus b should be what? A plus b. Just say a times a is what? A squared, isn't it? So root a times root a will be what? Root a squared. Square will cancel square root, and that becomes what? A. Basically, the root of a number times the root of that number will be that number. Okay, so the root of a number times the root of that same number will be that number. Okay, so that we have the limits as b tends towards 0 of this by this is going to be a plus b, and this guy next will now multiply this guy. Then we're going to have plus root a times root b. Root a times root a times root a plus b. Then this guy will now multiply this guy, becomes minus root a into bracket root a plus b, similar to what we had initially. Then minus times plus is going to be minus root a times root a is going to be what? A all over b into bracket root a plus b plus root a. Okay. Now, of course, you understand why we are rationalizing, right? Because if you make b equals 0 here, this guy is going to be undefined. Okay. So we take the limit as b tends towards 0 of this, and then we'll have, you see that this will give us 0. Is that okay? Because it's the same expression, and it's positive and negative all at the same time, so it's going to give us 0. So invariably we have a plus b minus a all over b into bracket root a plus b plus root a. Okay, so in this case also a will subtract a, and then we have b over this. So our function becomes, we have the limit as b tends to 0 over our function b over b into bracket. If b opens this bracket here, I'm going to have root a plus b plus root a. Okay, so from here, what do we do? What we're going to do is, okay, we're going to see that b is here and here, right? So we just cut through. Okay, so our function will now become the limit as b tends to 0 equal to 1 over, because b has taken care of b, 1 over root a plus b plus root a. So let's now make b equal to 0. If b equal to 0, so then our function becomes 1 over root b is 0. So we have only a left plus a, root a plus root a. Okay, this becomes root a plus root a. It's going to be what? 2 root a. We have 2 root a's. So it becomes 1 over 2 root a. And that is going to be the answer. Alright, in the next video, I'm going to be using the L'Hopital's rule, which is the fourth technique of solving limits, of evaluating limits. We call it the L'Hopital's rule, or L'Hopital. The L'Hopital's rule. Alright. Okay, I could just show you what it's about. Now, look at this expression. So the L'Hopital's rule now. Look at this expression. The limit of x squared minus 4 over x minus 2, for example, as x tends towards 2. You know we could use factorization method here. Now, in this case, if we use factorization method is an alternative of L'Hopital's rule here. Now, one thing you should know is first is this. L'Hopital's rule only work when your function will become indeterminate if you substitute. That is, if you have tried, L'Hopital's rule should not be your first option. L'Hopital's rule should always be your last option when you have tried other methods. And he keeps giving you 0 over 0 or infinity over infinity. Okay? So, and if you see this, in this case, if you solve this guy, substitute this guy into this case, it's going to be 2 squared minus 4 over 2 minus 2, which will give you 0 over 0. So in this case, L'Hopital's rule can work. Okay? So the idea of L'Hopital's rule is this. Differentiate both numerator and denominator until we can no longer get 0 over 0. Okay? So we're going to take the derivative, dd's dx, and dd's dx. So for those of you that don't know how to take derivative at all, our next topic is going to be derivative, and it's going to be very simple. So just follow along, at least for now. So derivative of this is going to be just use this guy, bring it down, and reduce the power. Is that okay? So you're going to have 2x minus, by the time you differentiate the constant, you get 0. Just calm down for now. Differentiate the constant, you get 0. You differentiate a quadratic term, you get linear term. So that's why we're having 2x here. Over differentiate here, you're going to have 1. Exactly. So you can now take the limit of the function as x tends towards 2. So if this is the case now, you now have 2 into bracket 2 over 1, which is what? 4. And of course, that is what we'll get if we had solved that using factorization method. So you see, the L'Hopital's rule also worked. The next video, I'm going to do more questions using the L'Hopital's rule. God bless you if you stuck till the end of the video. And do well to share the video with your friends and subscribe to the channel, please. God bless you. Subscribe to the channel.